More astrophysics. Today, we'll talk about what keeps our sun and all stars stable, this balanced thing between radiation pressure and gravitational. Define a couple terms, luminosity and apparent brightness, and we will work some problems with this Stefan Boltzmann law and Wien's law, however you want to pronounce it. Fortunately, our star, the sun, is stable because there's a balance between what's pulling it in and what is pushing it out. All stars are going to be powered by fusion. Ours is mainly fusing hydrogen together right now, and that's going to cause this radiation pressure that is pushing out. This is the radiation pressure that's causing this. However, as you probably know, our sun has a lot of mass, and that mass is being pulled in by the gravitational pressure. And what keeps our sun stable is you have a balance between those two that keeps our sun at the size of it is. Now when stars swell to red giant size, there's no longer a balance during that growing, and with Cepheid variables, they're bigger and smaller. Also, there's not this same balance, but our sun is nice and easy because of the balance. All stars have a luminosity that you need to be able to measure. And so, definition of luminosity is this: power radiated by a star. And in fact, when you see the word luminosity, if you just want to think of it as power, then that would be a fine thing to do. Keep in mind, this has nothing to do with how far away it is. It just depends on how powerful that star is, wherever it happens to be sitting. And as you probably won't be surprised by, this depends on its size and its temperature. Big, hot things are more powerful than small, cool things. We'll get into an equation later on. And so, since it's power, you can probably guess it's measured in watts. Our sun, which often is a standard, has a power of about 3.8 times 10 to the 26th watts. You don't memorize that, but it's good to have that written down somewhere. Sirius, which is the brightest star in our sky, has a much bigger luminosity, about 25 times that of our sun, but it's nowhere near as bright because it's so crazy far away. So remember, luminosity does not necessarily relate to how bright it appears, because stars are different distances. Rigel, which is nowhere near the brightest, it's bright, it's in Orion, but it's not the brightest star in the sky, is something like whatever the sun's is times a magnitude of 10 to the 4th, because it's ridiculously giant and powerful, but it's not as bright as Sirius because it's farther away. Now Venus is going to have luminosity of not much, because remember, it's just a planet. It's not on fire. It's very warm, but there's no fusion that it's putting out. We can see it because it's reflecting light from the sun, but its luminosity doesn't compare to that of a star. When you are looking up at the night sky and you're wondering which stars am I going to be able to see, more importantly than luminosity might be the apparent brightness, because what apparent brightness tells you, as its definition, write this down, it's how much power you get per unit area that you receive based on where you are at in the universe, which very much does depend on how far away the star is, and it also depends on its luminosity or its power. Now the equation for this is going to be that power or luminosity divided by the spherical area surrounding a star, which is 4 pi, and the radius or the distance you are away squared. So based on this, you can probably guess the units will be watts per square meter. And you can also think of this as like an intensity. And if you want to look at some numbers, the apparent brightness of the sun is about 1400 watts per square meter. If you just did topic 8, you might remember that as the solar intensity that you used for some solar energy problems. Now, Sirius, I don't actually have the numbers on this, but it's going to be way less than the sun. Even though it's crazy powerful, it's way, way far away. And Rigel, which is a ridiculously powerful star, is even less than Sirius. It doesn't appear as bright, and that's because it's so crazy, crazy far away. Now Venus, which we said had almost no luminosity because it's just a planet, is sizable because it's very, very close, and it reflects a lot of the sun's light, so it's bigger than Sirius, bigger than Rigel, clearly nowhere near as bright as the sun. An equation for looking at the power or luminosity of stars is a pretty straightforward equation, and that luminosity can be calculated with this equation, which is the first one in your IB data booklet. With LB and luminosity, you know that. This is the Stefan-Boltzmann constant, which is this number. It's got the crazy units of watts per meter squared Kelvin to the fourth. You can probably guess that A is going to be the area, surface area of your star, and this is your temperature, obviously in Kelvin. At least it's obvious to me. Often you can be asked to solve a luminosity mathematical problem, and more often than not I find that they are ratio problems, but you just need to figure out what value is what. So for example, read this, pause it, try and solve it. Now, the key facts are given you. The luminosity of our sun, which is often an L with a little circle with a dot in it, is at 3.9 times 10 to the 26. The 6,000 K, that's the temperature of our sun. And then the radius of our sun, we're going to take as a constant. And then they also give you that this other star, which we're going to call that, is the 4,000. It's much cooler. And if you look at its luminosity, it's ridiculously big. It's about 100 times more powerful than our sun. So you can make a reasonable guess. If it's cooler, but much more powerful, then it must be massive. So whatever radius of this guy that we find, it better be bigger than our sun. So we use our luminosity equation, and stars are spheres. So you should know to plug in for A, equation for a sphere. And for our sun, we are going to have these values. Now we're going to make a ratio, though, and compare it to the luminosity of whatever mystery star this is. And we're going to have the exact same equation. But we're going to use the radius of this mystery star. And now you should notice that you have some nice things canceling. Let me change colors. Those go away. And you end up, once you do a little bit of algebra, with the ratio of this new star. And you have to work this algebra out yourself, but it's going to be this value squared, this one, luminosity, the other star, all divided by this temperature, that star to the fourth, and this luminosity. Once you plug in the numbers and you do the math, you will find that the radius of the star turns out to be about 26 times the radius of our sun. And that makes sense, because if it's a cooler star but much more powerful, it must be bigger, and this is saying that its radius is 26 times the radius of our sun, which is enormous.